way I have graded is if you have done a calculation, numerical error, then I took some small half or 1 point off. But if you had a wrong formula, or if you had done something otherwise wrong, principally wrong, then I've taken more off, right? 1 or 2 points. So that's how I've done. Okay. That takes care of that. So let's go on and two things. Thinking. What we could do, just to be sure, we can look at the, I have the solution for the test part B. Let's see, so I could go, we can do that real quick. Test part B. Yeah. So we have to calculate the relaxation loss from the point of stretching these strands to the pre-stress transfer, right? And so we have 5 days was our transfer day, right, where we transferred the stress. So I've calculated the logarithmic of 5 times 24 is 120, divided by 45. Now, if you've done 10, you should not be deducted for wrong formula, right? I'm not sure how consistent I was, but I took off as if 45 was the right answer and 10 was not. So let me know. And the FPI is given as 75% of the ultimate, so it's 202.500 pounds. Everything is pounds and inches, so that you don't make any mistakes of feet and kips and all that. So make sure everything is unit-wise consistent. Otherwise, there is nothing. The FPY is calculated from as 70, I forget, the 230 psi anyway is given, right? In your list, because I gave you all the information. Let me make sure. I don't think anybody missed that one. FPY is given as 230, right? So that's what this is, and this is the formula you were supposed to use, right? And then 3.2b, which is the elastic shortening loss. Now, this one, the way we had in the exam, I didn't want to penalize you, and I didn't mean to even confuse you with how these are interrelated. So they are done as if one doesn't affect the other, right? So for example, if you have calculated this relaxation, I have simply, because this happens before the elastic shortening, so it is obvious, so I took out the 3000 psi from there for 7 or 5 days rather. So your PI is now 2002.5 KSI minus this 3 KSI that we got for relaxation for 5 days, so that you are 199. And then so the formula is, of course, N times elastic shortening is N, which is the ratio of E versus ECI, right, or E of steel versus E concrete at the time of transfer, because the shortening is happening at the time of transfer, right? So that's the E you want to use. So E changes, yes, that's what the whole point is, that it changes from the A is related, so you don't want to use, in some of you did E use the, is the final E. You want to make sure you want to use the E for that stage, which is 2.73 is given to you, right? And if somebody calculated E based on the given compressive strength at the time of transfer, that's okay too. Because this was given doesn't mean you can't use the formula. So if you use the formula, that's still okay, you'll get a slightly different answer. But anyway, it comes out more than 2.73, by the way, if you use the formula for the ECI at the top of this page, right? So nothing extraordinary there. This is from chapter 1, basically FCS calculation, right, for the dead load, because dead load is applied right away. You don't have to wait, so at 5 days you apply the dead load. So again, let's see what else could have gone wrong, and I am trying to remember. Some of you might have done this, where this PI is the force, and some of you have used stress. So make sure you don't use stress where force is needed, right? Because PI is the force, and FPI is the stress, right? So you want to make sure you're consistent. That's the kind of mistakes I have seen, right? So you don't want to use FPI. So the stress is this based on this is the stress at the center line of the strand in concrete, and this is the conversion, because there is a strain compatibility, the strain in concrete is same as strain in steel, so that's why this is, right? That's why you have to multiply by the ratio of the two moduli. That's the reason, right? Okay. Then the relaxation for the second part, item C, is from 5 days to 5 years, right? That was what was asked. So it's the same equation, except now we are using these two values of time. That's the only difference. And then by the time you're using this, your FPI has reduced because of various things. So that is elastic shortening, and this is the relaxation up to 5 days. So your relaxation for the second part, which starts at 5 days, will start at this FPI, which is 185,000, right? So it's kind of, it's like you're depreciating your value, you're losing your pre-stress, so you keep account of that as you go, right? So at that stage, this is your PI at 5 days, and that's what you use. So once you include that, and the time factor, logarithmic, and whether you use 10 or 45 is equally good, you'll get this number. Now, if you use 10, then you'll get more like 10,000 PSI, which is okay now, and if I have deducted your calculation by half or 1 point, let me know, okay? Then equation D and E are very simple. D is for the creep, and so N is the ratio again, but this time this EC is the EC for the final value, because most of the time you will be, creep is it's a long-term phenomena that you don't want to use the initial ECI, right? You want to use the normal EC, which is higher value. So if you didn't do that, then you're not following through what we are doing here. So make sure this is the condition. And so FCS minus FCSD. Now, somebody could explain to me why we are subtracting from this to that? Anybody? Why we are subtracting this CSD? FCSD is stress caused in concrete, because it says C. SD is the superimposed dead load, right? So the reason for that is when your creep for the most of the time happens under the influence of superimposed dead load is already there, because we are considering years, 5 years, right? So superimposed load is already there within a matter of few weeks, right? Compared to 5 years. So you use this stress, and this stress is actually helping you, because we are calculating the stress in concrete at the center of gravity of the pre-stressed tendon, right? At that level, the concrete stress that was without the superimposed dead load is subtracted by this, because as you apply the load, your compression that you had is decreasing, right? So this is how much compression has decreased because of at the bottom fiber, or the fiber where you're calculating, right? That's why this is subtracted, okay? And this is the ultimate value. This is for the post-tensioning method, right? And then here is the last one, which is the shrinkage, this is a constant. This is a constant for depending on post or pre-tension. EPS is given, and then this is all volume of our surface is given, and then the relative humidity is subtracted, right? So make sure you don't do the other way around where you just simply put 75. So it is 100 minus 75, so it should come out to be that. So if you add up all this, then you get, the reason I'm adding up, I don't know if I didn't ask, but I had told you in the class that we should add all this up and see if it is in the ballpark. So if you didn't get in this ballpark, like 30 to 50,000, then you should go back and check your numbers. Somewhere you have done wrong, right? So this was not asked for. If you didn't do this, that's okay. All right, so that was that. Okay, so now we are ready for the remaining part, or theoretical part anyway, losses due to friction. So now what happens here, in this case, there are two parts. Number one, let's talk about what is losses due to friction. So when you stretch the strand or pre-stressed steel into a particular profile, if it is straight, then it doesn't happen, or very little happens, but usually it is a parabola or a triangular shape, right? Because of the curvature and kink, as you know, the friction value has to do with the normal stress, right? The mu, if you remember from statics, if you have a block sitting on this table and I want to drag it here, right? If I want to drag it, then the amount of force I want to apply to drag something on a surface depends on the normal force and the coefficient of friction. So if I'm dragging something on ice, for example, then I don't have to push too hard. That's why you have ice skating, right? But if I'm dragging something on a carpet, it's very difficult because it's tend to have higher friction, right? So that's why they put a Teflon on the bottom of your furniture, little shoe, so you can easily drag it, right? So to reduce the friction coefficient, and that depends on the texture of the surface, how rough and smooth it is, and what type of material it is, right? So anyway, so we have a friction coefficient. Friction loss is because where you have a kink or where you have a profile and you're trying to stretch it, it's going to rub on some surface somewhere, right? On the part that have the minimum and maximum points. So depending on, suppose in most of the time we are dealing with simple supported beam. So it may be a profile like this, or you may have a profile like that, right? But in many times your beam might be 2 or 3 spans. Now you have a profile like this, and you're pulling this way. So at these points, you are going to come in contact with the duct surface, right? So the friction comes into play because you're pulling from one or both sides, and you're dragging as you pull as you stretch the strand, as you saw in the video, you're stretching for many inches, right? So as you're pulling this, you're stretching it, you're rubbing against the surface that has these profile up and down, right? So you're going to have some friction loss here, some friction loss here, here, and here, right? As you pull it. So that's one part, which is called the mu alpha, where mu is the coefficient of friction that is given in the table. Alpha is the angle of the profile. So sharper the angle, bigger the angle, more is the loss, right? If this profile is, if angle is 0, then this force can go away, right? If it is a straight tendon, no profile, then this will be 0. Alpha is 0, right? And so KL is the other part, which is called the wobble. Wobble is the one, so right here, as I say on the top, curvature effect based on tendon form and alignment. This is the predetermined at the design stage. That means looking at the profile, you can tell what I got. If my profile is straight, then this part is 0.
Is the angle in radians or in degrees?
It is in, is it in a ratio? We'll see. It is closer to a radian, right? It is a ratio. This angle is the perpendicular to hypotenuse or perpendicular or base, perpendicular to the base, tangent, right? That ratio. It's not a real angle. It's a radian, if you will, right? So curvature effect can be calculated based on the profile. You can calculate that. The wobble effect, wobble means like your wheel wobbles, your car wheel, if it is not aligned properly, so it wobbles. It is a defect type thing, right? It's wobbly, the wheel is going like that, right? Shaking because your alignment is screwed up, right? So in this case, wobble effect is based on local deviations in the alignment. So if you have a straight tendon, for example, a straight duct, and you're pulling, you still will have the wobble effect because of the variations in the profile may not be perfect. And you may inadvertently, without any particular reason, you're rubbing against some surface because of the irregularities in the profile or defects in the profile because of, if your duct is very soft, for example, and you pour the concrete, so it's going to pinch into an ellipse that you thought was a circle, right? Or worse yet, somebody has really pinched it, now you're going to rub against. So it depends on the skill of the construction, for example, right? So it depends on how well you're done and what kind of material, soft or hard, you're using, right? So it depends on that. Or it could be accidental anyway, even if you had very good skill and somebody accidentally kinked the duct somewhere, right? Irregular surface. So because of that, the wobble effect is hard to eliminate. So this second part, which depends on the length times a constant, depending on what type you got, right? So these two combined together multiplied by the normal force. Remember I told you about if you drag something, it is dependent on the normal force or the weight. So we always have normal force multiplied by these two, right? And so the value of friction is dependent on the material of the duct and presence or lack of coating or greasing. That makes sense, right? Friction depends on these things, what type of duct you have. Where mu is the is given in table, alpha is the angle, which is 8y over x, which is, if you this is your y, and this is your x, or sorry, the whole thing, the length. So this is x and this is y. So 8y over x, and there is a explanation given in the book of how you reach this point. Tell you what it has to do with how much eccentricity you have in what length. So ratio, that gives you a angle, right? Bigger the y, in other words, bigger the angle. If the y is 0, then the angle is 0, right? And L is the length of the beam, and K is the wobble coefficient. Okay. So now, the other part is the anchorage seating loss. So anchorage seating loss happens in both. The first one we talked about, friction loss, is only in post-tensioning. What happens in pre-tensioning? Why not in pre-tensioning? Because there is no duct. There's nothing to rub against, right? There's no friction loss, there is nothing, right? So, but in this anchorage seating loss, it always happens because it, depending on the style of the wedges you use to seat the, like you're pulling the wire and you let go. As you let go, it grabs it. But before it can completely grab, because it has teeth on it, these wedges that surround your wire or strand has teeth, sharp teeth, right, threads. They grab because of the shape, right? So as they grab, before they can completely grab, you have slipped a small part, like 1/4 of an inch or 1/2 inch, right? So that creates the loss of strain and loss of stress, right? So it's typically in the range of 1/4 to 3/8 of an inch. It's given by the manufacturer to you, depending on the shape and how deep the teeth is and how much you're grabbing, how much you will slip before you completely stop, right? So this could be overcompensated. In other words, if you know how much you're going to lose, say you're going to lose about 1% or 2% of your pre-stress, you can put some extra pre-stress so that you get what you need, right? Provided, of course, you don't break the wire or get too close to the rupture, right? So you have a limitation on how far you can do. And this happens to both pre-tension and post-tension. Overstressing of the pre-stressing has to be usually done to pre-compensate, like I said. And this formula is very simple, right? This is, the loss is equal to the slip, which is delta A, divided by the length. So what does that give you? Slip versus divided by length is the strain, right? Strain divided by modulus is stress. That's simple, right? So strain multiplied by E gives you the stress loss. So this is very simple, really. It's the easiest loss that you can calculate. And is it short term or long term?
Long term. It's long term.
Is it a short term loss or long term loss? How about anybody else? Short term or long term? Short term?
Long term, I think.
When does it happen? During the pull, right?
Yes.
And does it continue?
No.
So then it is short term, right? So it is short term, it happens instantaneously, right? It's like elastic shortening, right? It's actually the first loss in post-tensioning or pre-tensioning. It's the very first, as soon as you stretch, well, I shouldn't say that. That's not true. It happens
During the wedge.
Jacking.
You jack and you release.
Yes.
Do you have, no, there is no loss before that, does it? No, this is the very first loss. The relaxation starts after this, right? Because you haven't stretched anything, so how can you start, right? And it's time dependent, it's not instantaneous. Elastic shortening happens at the time of transfer. So which one happens first?
It's the anchor.
This happens first, anchorage loss, and then you have elastic shortening, right? It's kind of simultaneous, but there is maybe a fraction of second difference, right? The beam is responding to the stress applied, concrete, but the load is not decided yet. The other funny thing about elastic shortening is you apply a force, right? Let's say you applied 6 million pounds, right? Say, or that's kind of big, right? It's 500,000 pounds. That's more like it. So you apply 500,000 pounds, and because of elastic shortening, you lost 10,000 psi. So the elastic shortening is based on 490,000 or 500,000 pounds. So you stretch the wire to 500,000, right? And you put the wedges. Now you got 500,000. It's not the jacking force. It's the 500,000 is the force after you lost the anchorage, right? Let's say that's the case. Now elastic shortening will happen, right? At the beginning of elastic shortening, your force is 500,000. I just gave you a number. But after the elastic shortening, it is 490, right? So I should be using 490 really, right? My strain is dependent on stress. Applied stress is 500 or 490. I thought I will put 500, but I ended up with 490 because I lost because of the shrinkage or shortening of your elastic shortening of your concrete member. So the applied force is 490, right? So the elastic shortening should be based on 490, right? But if I put 490 as my applied force, it's going to shorten in a different manner. So 490 is not accurate, right? So you can keep on doing this. It's like the perennial problem that will not end if you are very, very accurate. If you want to be accurate, you'll have to do it many, many times. So it's a matter of what is accurate, how much error you want to allow, right? So you could simply apply 500 and forget about changing. That's one way of doing it. Remember, I told you at the beginning, we are not looking for accuracy, right? But you can try that just for fun, right? So we will see in the example, when we do the example, that it really doesn't matter a whole lot in the scheme of things, right? Okay. So that's the loss, that's the second loss, right? Let me see if there was anything else left here. Oh, this one last thing, yes. Change in pre-stress due to bending of member. So what really happens is, as you apply the stress, you are actually, let me see. You apply the pre-stress, you apply the loads. When you apply the loads, excluding, well, let's see. There is a difference in behavior of, when you talk about relaxation loss and creep and shrinkage loss, especially creep and relaxation loss. The live load is not included in all this. Remember, when we are calculating the loss for creep and relaxation, we are talking only superimposed and the other dead load, right? That's all we are talking. Why are we not talking about live load?
Because they are time dependent.
Sorry.
They are time dependent.
It's changing.
It will affect, but we are neglecting. It is a transient force, like a wind, for example. It's a transient load, right? It comes and goes. We are looking for something that is either permanent or close to permanent, right? That's what we are looking. We're looking for sustained load, because creep. If I put a load for a few seconds or a couple of minutes or even half an hour, it will affect the creep. The creep will be more. But in the scheme of things, when you are talking 5 years, what is half an hour or even 1 day, right? Nothing. So what we do is we disregard the live load.
Excuse me.
For relaxation.
How can I categorize, for example, if I'm designing and I'm looking at the service loads? How can I categorize, like, for example, assume a slab down, the students who are going to be using this classroom. How do you categorize? Are they superimposed loads or are they live loads?
Very good, excellent question, I have to tell you. Everybody gets confused. The word live and dead is not good, in my opinion. We should be calling them sustained load or transient load. That's what we should call. Like, for example, wind is a transient load. It comes and goes in a matter of minutes or hours, maybe at the most. Earthquake load is hopefully in matter of minutes, right? You don't want to have more than minutes, right? So it is also a transient load. But when you say live load, many times you use loads that are not quite transient when they are still called live load. So that's why you asked a question, and I have to tell you, the right vocabulary should be sustained load and transient load, not live and dead. For example, this classroom, the furniture is a live load. Why is it live load? Because it moves around. Sometimes you have more furniture. In a couple of years, this may be something else, right? This room may not be a classroom. It may be a seminar room with hardly any furniture or lighter furniture or what have you. It's changing. But it still has a minimum value. But if you know that for next 5 years, this classroom is going to have this kind of furniture, then might as well call it sustained load and use it in your calculation for creep and relaxation.
Actually,
Shrinkage doesn't matter because shrinkage has nothing to do with.
That's where I was getting confused when you're calculating
Shrinkage.
the creep.
Creep, yes.
Yes, because
Because it was given the live load.
the
but
live
we
load,
didn't
and I was
include the
comparing
live
them
load
to
in
this
the-
service load.
No, live load is generally transient, but some live load is not transient. That's the problem. So you have to say, okay, I'm going to use 10% of the live load as a permanent load or sustained load. Then I will understand your logic. But if you put the whole live load, that is an overkill.
That was my assumption. By the way.
That will be an overkill because all live load, most of the live load, or depends on the structure. Some structure, like you have a bridge, for example, because that's where you use pre-stressed concrete a whole lot. The live load comes and goes, so it's not sustained. It comes and goes away, then comes and goes away, right? So it may not be even 50%, right?
How to spell transient?
Transient and
Yeah.
sustained. Sustained means it's there permanently,
How to
or at
spell
least,
it?
huh?
How to spell it?
Well, how to spell? Okay.
Transient.
So transient. I could be wrong. And sustained.
Okay.
Okay. So these are the two. Transient means comes and goes. Something just comes and goes. And sustained means I'm always there, right? You hold it fixed, permanent, right? That's sustained. So that's a debatable thing your textbook is doing. And in the whole industry, that's the same thing.
Actually, when you use BS, BS is they categorize live loads, including the wind and everything is under live load and everything. Basically, everything which comes and go. Even these are categorized to be live loads.
Live load, right?
Yeah. So now, still the same case I was going to apply when I was doing the previous assignment. I was going to say all live loads supposed to be included in calculation.
You have to explain to me what your thought process is. If you
But now
just apply,
I've got a new concept. I've gotten it now.
you got it, right?
Yeah.
That's the most important part. We are all. Yeah, I looked at all these your exams and and assignments and all, and I know some confusion, and it is a confusion unless you understand what affects you and what doesn't affect you. So I think when you talk to geotechnical engineers, for example, they don't use live and dead load. They use transient load and sustained load. That's what they say, and I agree with that because for geotechnical engineers, it's the same phenomena, especially if you're dealing with clay type of soil, because clay responds time dependently. And sandy and silty soil do not depend on time. Your response is right away. As soon as you apply the load, there it is, right? So if you have a settlement, then the settlement is immediate if it is a sandy or gravelly soil, right? If it is the clay soil, especially expensive clay, then it is a different behavior. Now, we are not teaching or discussing geotech here, but our material is like that. Our material behaves like clay or wood, time dependent, sustained versus non-sustained loads. So that's why we need to check. So here, what I'm saying here is change in pre-stress due to bending of member also talks about FCSD, the stress in concrete because of sustained or superimposed dead load, or sustained or dead load, right? This should be sustained. That's where I got stuck. I said, let's clarify what we are talking here. At least philosophically, we should know that it should be sustained. And if you are doing your engineering, your own, and you are 100% responsible, then you should clarify that. Hey, if this load is permanent, call it live load if you want, then I better have it here, right? So this sustained load, what it does is, when you have a sustained load relief, this superimposed dead load is the stress at the center of the tendon in concrete because of superimposed dead load. If you divide that by E, then you get strain in concrete, and because of strain compatibility, that's a strain in negative way, reducing the length in the tendon or in the strands. And this strain multiplied by the modulus of the steel, pre-stressed steel, it gives you the increase in stress as opposed to gain in the strength, because you're actually doing a tensile. Your concrete is being stretched basically. Your compression is reducing or you're stretching. Tension is net. There could be a net tension even in concrete that is allowable, right? So you're elongating the strand or the pre-stressed steel. Because of elongation, you're gaining this much stress, right? So there is a gain, is what I'm talking about. All right. So this is I wanted to make sure. So there are 3 items we have discussed: the anchorage, seating. We talked about the friction, and then this is a negative loss. This is a positive. This is increases somewhat.
Is it significant anyway?
Huh?
Is it significant?
No, it's not. It's considered because it is significant. It is not as much as creep and shrinkage, but it is still there. It's comparable to the anchorage seating loss, for example. Okay. Because that also has to do with strain, and this has to do with the strain. So, okay. All right. So I think that's what we have as far as theory is concerned. Let me see if there is anything else. Now, the next topic is chapter 4, which is flexural design, and I'm just going to talk one more time just to keep your interest. But really what we are going to do after chapter 3 is this part, where you're going to flexural design of pre-stressed concrete elements. In other words, we are going to select the cross-section. We are going, just like we do in regular concrete, in reinforced concrete, we are given loads and we are supposed to find out the cross-section and how many rebars you need. We are going to do something similar. What should be the cross-section among the tabulated shapes, for example, right? And what should be the pre-stressed, how many strands do you need and what grade they should be? This is what we will do, right? So here's the design pre-stress element is primarily controlled by flexural stresses, not by shear, right? Trial section is selected using transposed version of basic equations, and just keep that in mind. Our basic equation says the stress is equal to the applied pre-stress force, the eccentricity, the section modulus, etc., right? And the bending moment of the superimposed dead load and all that, right? So there is a section modulus in there on the right-hand side. So if you transpose the equations, then section modulus could be brought into the left side where the stress are FT or FB. You can have ST or SB and then all the other stuff on the right-hand side. That's the general idea. And then you do it such that your stresses, now here's the difference, and we will talk more about that. The further adjustment, the trial section is finalized along with tendon profile. During such adjustment phase, it is ensured that the section can safely carry the pre-stressing force and intended design loads. Safely carry means you want to not exceed the stresses in the tendon and in the concrete, both steel and concrete, right? In reinforced concrete, it is sufficient to design a section for limit state. That means I'll give you the bending moment, factored bending moment, and that's it. You find out what rebars you need. Here, it goes in stages. You want to check when you're transferring the force, pre-stress force into concrete. You want to make sure your stresses in the strand is not exceeded by a certain amount. Your stress and compression in concrete is not exceeded by given value, and so is the tension. Unlike reinforced concrete, in pre-stressed concrete, additional checks are needed at load transfer, at limit state of service load, as well as at limit state of failure. So at least 3 stages. In fact, there are more stages. This is the simpler version. The failure load in pre-stress case indicates reserve strength. So this failure part, this last part of the limit state, is a reserve. You can stop at the service load and not exceed the stresses. This tells you how much more can it take before it actually snaps, right? So that's what that is. The failure load in pre-stress case indicates reserve strength for overload conditions. These checks ensures that for service load, the cracking is negligible and the long-term effect of deflection and camber are well controlled. So we want to check deflection, we want to check cracking is not happening, all that, for the service load. For ultimate or limit state, of course, cracking will happen and the section is going to behave like a reinforced concrete section. After the finalization of geometry and tendon, other requirements such as shear torsion, deflection, etc., and cracking are all checked. But this is last part, after you select everything, right? Let me see if there is anything else to discuss. Well, let's take care of this also, and then we'll get into the formulation next time. So another way of looking at the difference in the approach, in the design of, because you guys all have done reinforced concrete, so just to see what's going on, what is different is what this is emphasizing. The approach in design of reinforced concrete element versus pre-stressed concrete is, while in the reinforced concrete case, one can consider external load being applied simultaneously. So your live load, your dead load, wind, everything is applied simultaneously in various combinations according to the code, but one time, at one stage. And what is that stage? 28 days compressive strength, that's it. After that, you don't care. So that's that, right? Simultaneously or sequentially in some cases, after the design compressive strength, F prime sub C is achieved, 28 days. That's all you look at. The intermediate values of the stresses would not influence there may be you know, like you haven't reached 28 days, you have put some load, the self weight could be put, but you're not checking that. You're checking as if it is 28 days, right? To summarize, in the case of pre-stressed concrete elements, this is same thing said differently is what I'm saying. In this case, pre-stressed concrete case, the stresses have to be calculated at various stages and kept within the various specified limits per the code at various stages. And we talked about three: the transfer, the long-term, and then ultimate, service ultimate, right? So three for the service loads. This is followed by stress calculations corresponding to the failure. That's the last thing you check. So to look at in terms of sequence, this is what happens. Application of initial pre-stress to the you just simply jack the stress, you just stretch it. That's the first step you do. What happens at that stage? You start relaxation losses right away, right? Transfer the pre-stress force to concrete element. This generally involves applicable short-term pre-stress losses such as anchorage seating loss, relaxation loss, for pre-tensioning anyway, right? For post-tensioning it doesn't happen because it happens only at the transfer, it doesn't happen at jacking, because that's simultaneously. Elastic shortening, friction for post-tensioning case, right? So all this happens in the transfer of pre-stress at that stage. Then application of self-weight of the concrete element as soon as transfer of pre-stress happens. So this is almost instantaneous right after the transfer, right? So the beam goes camber up and then the weight pulls it down somewhat, right? And then we have application of superimposed dead load. That's the next stage. At that stage, so you're putting a floor on top of your beam. At that stage, if you are okay at the transfer, you may not be okay here, because some stress may be too high, right? So you have to check this. Application of full service load and long-term losses and gains, or actually there is only one gain. I don't know why I wrote gains, but this should be singular. In some cases, due to additional tension, like I discussed, right? And overloading under certain conditions up to the limit stage, if you expect overloading. Let's check out how much overload can I go beyond, right? So all this, these are the stages we have to consider in post-tensioning or pre-tensioning, in pre-stress concrete in general. I think that takes care of, yeah, this gets into more stuff we will talk next time. So let's see, it's 7:30. So I'm going to take a brief break and we'll be back in a few minutes, okay? We'll look at something. And it's okay? I need to look at something here. Anybody else has any question on the return grading, let me know, okay, at the end of class? You don't have any question, just want to make sure. Yeah.
I want to take some points on.
I don't think so.
Maybe like a 36 out of 40. Do you think your rating's superior? Because I had to redo the problem like 1,000 times. Like whenever I was doing my calculations, I always forgot like a thing. Every time.
有些上次就是这些都是对的，但是结果是错的。就是我跟你说，我觉得太看了吧，结果他本来就是那样，我不该改的，不改还是对的。